What you see on the screen here is an equation that represents conservation of momentum. Now it's horrifying looking. Look at all that subscripts and all that stuff going on. It's not that big a deal, you guys. If you look, you've got on both sides two different masses, mass 1 and mass 2. And then you've got what looks like V10. That's actually V10, which means V1 initial, the speed when time is equal to 0. And V20, which also means initial. So just so you know, the zeros mean initial. On the other side, you have mass 1 and mass 2, but you also have V1F and V2F, which means final. So in essence, what we have here is the momentum of one object and another object before they interact with each other. In other words, before they exert forces on each other by colliding or in some other way, pushing off each other. And the same two objects having momentum after. So those are the momentums after the interaction. In other words, let's say I had a car hits another car. The car is going to have some momentum. Let's call them car A and car B. Car A has some momentum before the collision, and car B has some momentum before the collision. And they're going to run into each other, and something's going to happen. You know, maybe they'll bounce off each other, maybe they'll hit and stick together, who knows. But one thing I do know is that they can't hit each other without changing both of their momentums. So afterwards, you're going to have some kind of new scrunchy cars that are having different momentums. And again, maybe they stop. Or maybe one of them's got more momentum than the other one to begin with, and they move off at a slower speed together after the collision. Who knows? Bottom line is that change in momentum is equal for both cars. So whatever momentum A gains in the process, or loses in the process, depending, is gained or lost by the other one. There's three different varieties of problems we're going to do, and I'm going to show you all three. So let's start with the first one, which is the simplest problem. It's called a recoil problem. In a recoil problem, you have two objects that are together, then push off one another, and wind up being apart. So I think in your conceptual worksheets you had two spheres that were connected by a spring, and then you fire off the spring. Okay, now we know the impulse is equal and opposite on these, and which means their changes in momentum are going to be the same. If we look at this in terms of the equation that we had before, m1 v10 plus m2 v20 equals m1 v1 final plus m2 v2 final. Before I fire these things, they're both sitting at rest, which means this is 0 and this is 0, which means the whole expression is 0 and the whole expression is 0, which means essentially the entire left side of the equation is 0. We have a total combination of 0 momentum before we fire these things. Now afterwards, they're going to recoil. One's going to go one way, the other's going to go the other way. They will both have momentum, but it will be equal and opposite. Equal and opposite momentums mean that the mass times the velocity for each one of them is going to add up to the same number, or I should say multiply up to the same number, and they'll cancel each other out. So if mass 1 is bigger than mass 2, it'll have less speed than mass 2. Okay, the next special case we're going to look at is what's called an inelastic collision. That's when an object runs into another object, but instead of bouncing off, they stick. So they move together afterwards. If we write out our basic equation again, what happens in this equation is because the two objects move together at the end, they share a common velocity. In other words, there's no v1 final and no v2 final. There's just v final. So we could say that the two masses together are moving at one speed. And if I go back and put my left side back in, this is what you get when things hit and stick. Okay? Now it could be that mass 1 is moving and mass 2 is at rest. If that's the case, then V20 will be 0, and you would get even a more special case of this. But that doesn't have to be the case. They could move, this one A could be moving faster than being catch up and hit to it and stick, or that'd be like maybe in the case of railroad cars coupling, or you could have them moving towards each other and hit and stick. Maybe like when a football player tackles another football player. So, but at the end of the day, if they move together afterwards, this guy here is the equation you want to use. And you just plug the numbers in and solve for whatever the unknown is. Now, the final case is when things bounce off each other. And what you have to do is you just have to go back to our original equation. Our big original equation. And you would put all the numbers in that you have and solve for what you need to have. I could do a million examples, but at the end of the day, you just have to organize your information, figure out what your masses are, or if you're supposed to be solving for those masses, find your speeds. I would list all this information off to the side before I start. Okay, look at the problem, read the problem, get all this information. Some of these things will be zeros, not the masses, they're not going to be zeros, but some of these speeds might be zeros. The ones that are zeros, write a 0. If there's something that we're solving for, so let's say we're solving for the initial velocity of one of the objects, put a question mark next to it so you know what you're solving for. At the end of the day, that's just good problem solving technique. So go ahead and give those kind of problems a try. There'll be a couple of them on your quiz, and I feel like you'll do pretty well.